from addition law of vectors, fine, which is discussed here. So now we are concerned with the acceleration of this very particle, whether it is acted upon by some force or not, because from the second law of motion we know that if this particle is acted upon a force, then ultimately that will definitely cause an acceleration inside that body. And if the acceleration is zero, is not observed, that means the force is not there. So we have to observe, we have to observe this kind of stuff here, that whether the force is applied onto this body or not. So to get that acceleration, we know the acceleration is the double differentiation of position vectors. So with respect to this O, that is the inertial frame of reference, we will calculate the acceleration of this body, and for that we have to differentiate it twice, that is the double differentiation of this very thing with respect to time. So first of all, we will differentiate this very equation, differentiating this very equation with respect to time. Okay, so that means we will get our position vector, this differentiation, that means dot. I have already told you that this is the representation of dr by dt. Dot means differentiation of the vector with respect to time. Okay, so I will shortly represent it now onwards dot. This is not so much because it is shortly represented like this. So this is equal to this. R dot will be equal to this very R dot. Change of this, because we are considering this as the non-inertial frame. Okay, non-inertial means it does not follow the law of inertia. That means it may be accelerated with respect to this very thing, and we will get the acceleration of this very body, of this very frame of reference with respect to this, and that is given to as acceleration of s prime with respect to s will be the double differentiation of position vector r, here r, with respect to time. Okay, this will be the acceleration of frame of reference s prime with respect to s. So applying it onto here, first we will differentiate with respect to time. So we will get dr by capital R, dr by dt, that is r dot, that is the velocity of this very frame of reference with respect to this, because r dot means velocity, plus r prime dot. Okay, so this very thing will give the velocity of the particle, this particle in frame of reference s prime. Okay, now we are concerned with acceleration. So till now we got velocity in the frame of reference s equal to velocity in the frame of reference s prime plus velocity of the frame of reference s prime with respect to s. I have drawn this is s prime, frame of reference with origin O, and this is s with respect to, and its origin is O prime, so its position vector is r, and a point considered here, say its position vector with respect to this very thing is r prime, and with respect to inertial frame of reference its position vector is r. Okay, so the velocity comes out to be v will be equal to v prime, that is with respect to this very frame of reference s prime, plus v0. This is the velocity of origin of non-inertial frame of reference with respect to inertial frame of reference. So again differentiating, again, because we are to calculate here, to calculate the acceleration, again differentiating this very equation with respect to time, because acceleration is the double differentiation of the position vector. On single differentiation we get the velocity. Now we will double differentiate it. So we will get the double differentiation of r, that is r prime double prime or double dot, that is the acceleration, that is dv by dt, that is acceleration. Okay, and this acceleration is the acceleration of this particle p with respect to frame of reference s. Okay, plus is equal to acceleration is equal to v prime. V prime is the velocity of the particle p with respect to origin o prime, that is in the non-inertial frame of reference. So we will get acceleration, that is the differentiating this very thing, that is acceleration, velocity again, we will get acceleration but in frame of reference a prime, in the frame of reference s prime, plus v0 is the velocity of this frame of reference s prime frame of reference as a whole with respect to this frame of reference. So differentiating the velocity of the frame of reference s prime with respect to time, we will get the acceleration of frame of reference with respect to origin o. So this is the acceleration, this is the acceleration of this particle p in s, that is inertial frame of reference, inertial frame. Okay, so this gives the acceleration of the point particle p in the frame of reference s, and this a prime, it's a vector quantity, this a prime is the acceleration of p point particle p in the frame of reference s prime, in s prime. Okay, and this very thing a naught is the acceleration of the frame of reference. This is the acceleration of the frame of reference of the frame s prime with respect to s, because this very frame of reference, it is moving with respect to origin a with some acceleration a naught. Okay, so it has got acceleration of a naught with respect to origin a. So this o prime is accelerated, and this very acceleration gives generation to the forces which are called as the pseudo forces, which we'll discuss in a bit later time. Okay, so till now we have got this very acceleration. So for any two frames of reference, if we have inertial frame of reference and a non-inertial frame of reference, so in that very case we will get the acceleration of a point particle in the frame of reference, inertial frame of reference, equal to be the acceleration, the actual acceleration which is caused onto the body inside that non-inertial frame of reference, plus times the acceleration with which the frame of reference itself is moving. Okay, so this gives the acceleration of that point particle. Now we have to consider, we have to calculate the force acted onto that very point particle. And to calculate the force, we know we have to apply the second law of motion. Second law of motion says that force is equal to mass into acceleration. Mass times acceleration gives the force.